A very nice talk. And moving on to our last speaker of the day, a keynote speaker, Alexandre Bouchard-Côté from UBC. Alex did a PhD in computer science with an emphasis on statistics and also, I think, a minor in linguistics at UC Berkeley under the supervision of Michael Jordan and Dan Klein. He then joined the University of British Columbia in the beautiful city of Vancouver in 2011, where he's now an associate professor of statistics. And I think with the NeurIPS deadlines just passing this week, I think it's nice to mention that he won the Best Student Paper Award at NIPS in 2011, I think. So good luck to everyone who submitted papers there. His research focuses on Bayesian data science, a lot of phylogenetics as well, and non-reversible sampling methods, which will also be what his talk is going to be on, scalable approximations of integrals using non-reversible methods. It's a pleasure to introduce you, Alex. The stage is yours.
Thank you. Is the sound good? Can you hear me?
Yeah, thank you.
Perfect, great. Well, first of all, I wanted to apologize actually for missing many talks. So it's, I guess it's I should say I'm in the Pacific time zone. So with kids, it's a bit hard to work outside the regular hours. But just wanted to congratulate the organizer for a fantastic program and thank you, Torben, for inviting me to talk here. It's a real pleasure. So let me share my screen now. Okay. Can you see the slide?
Yeah, that looks good. Yeah.
Perfect. And can you see my arrow as well?
Yes. Yeah.
Perfect. And also, I just want to remind everybody to send your question as I talk to Torben, and I can please feel free to interrupt me. I can take question anytime. So this talk is about integration, computing integrals. So it's integration was invented 300 years ago. Yet it's still an area of very active investigation. Why is it still hard? So there's many reasons. One of them is when integrals are over complicated space, then actually often you can, the problem is probably hard. And this talk is about the continual quest for better integral approximations. So there are two main flavors of integrals that you've learned already. So Riemann's definition and Lebesgue's definition. And I don't want to talk so much about the definition here, but rather about the kind of assumptions that are needed for these definitions to make sense. So let's start with Riemann's version, where the input space has to be in RD. So this is sort of something that's essential to define it. And this has been the focus of lots of recent work, what I call sometimes the autodiff frenzy, that uses maybe a bit more information about the function, like differentiability, and have led to great results in the recent years. With Lebesgue's definition, we actually don't assume anything with the input space. The only thing that we really assume is the output space has to be the real. And the sort of what I find interesting with this definition is not really all the technical details, but really that sort of switch of perspective, that all you need is the output space to be the real. And so this will be the focus of this talk. I often think about that area, that sort of more general setup, as being relatively neglected, but I was really happy to see that there's attend this other talk by Samuel earlier that's also tackling this more general setup. And that was there was already several motivation for that more general setup in the earlier talk, but I just want to briefly mention one that which is dear to my heart, close to my heart, which is phylogenetic inference. And so the basic sort of version of that problem is to try to infer the tree of life. That's the one you might be more familiar with. So the object of inference is this discrete tree along with branch length internal events. In the recent year, one sort of a new frontier in that field is to do the same kind of inference, but for cancer cells. So a cancer cell they follow evolutionary dynamics, and we can ask the same question: can we reconstruct the trees of these cancer cells from copy numbers? So variation in the number of copies of each location in the genome. So I'm not going to go too much in details, but if people are interested, I can tell you more at the end. I just wanted to motivate that there are many situations where in applied statistics where we want reconstruction of combinatorial objects with, crucially, we want also a measure of uncertainty. We don't want just one tree, for example. We want to know certain part of the tree might be less resolved than others. We want to know that. So the Bayesian approach is very well suited for this. So it's based on computing a posterior distribution, where essentially that's an example where we use the power, the flexibility of Lebesgue integral, where here X could include in phylogenetics, for example, both the tree, so the discrete part, as well as continuous parameters. And here pi is the posterior distribution. So a distribution over maybe trees and parameter, for example. And then var phi is a statistic of interest. So this could be things like whether a subset of leaves in a tree form a clade. So have a common ancestor such that if you cut the edge above it, the group of species form is a set obtained from this process. So this is this last bit, the statistic of interest, which brings the combinatorial space back to the real. So at the end of the day, we always compute an expectation with respect to the real, but the input space X might be this mix of continuous and discrete quantity. All right. So the setup is the same as in Samuel's talk, but I'm just gonna introduce a bit of notation. So the target density is often only known up to a normalization constant. So there's a part on the top, let's call it gamma x, which you can compute for any given point. But to get a posterior distribution, you would need to divide by the evidence, which is the probability of the data, which involves integrating over, summing over all trees and integrating over all branch length and maybe evolutionary parameter. So that's the hard part, right? So X is the unknown part. So think about a tree and maybe some unknown parameters. We can forget about the data for now. Just remove it from the notation, because in the Bayesian framework, it's viewed as being fixed. So what we want, the sort of first step into Monte Carlo is that we're going to say we're going to approximate these integrals using a law of large number. Okay, just averaging a collection of samples, a collection of sample trees, for example, applied to this test function applied to them. We average them, and we want this to go to the quantity of interest as the number of MCMC or Monte Carlo sample n goes to infinity. So this going from Monte Carlo to Markov chain Monte Carlo is done as follows. With Monte Carlo, we just reduce the problem of integration to that of sampling random variable xi's, such that a law of large number holds. And now let's think a little bit about which law of large number. We don't want just a basic law of large number for independent and identically samples, because sampling from IID variables, so IID phylogenetic trees, is often as hard as integration. So the key idea here is that we're going to look instead at the law of large number for Markov chains, where now we want to build a Markov chain over that space of interest with stationary distribution pi. And that's really the key idea, that in some cases allows us to beat the curse of dimensionality, essentially. But this relies on being able to build a Markov chain with this prescribed stationary distribution. So just a quick background on this. So the typical way to do this is using reversible Markov chain Monte Carlo. So it's the good old gold standard for Bayesian computation, but it can be slow. So Samuel talked a little bit about reversibility and non-reversibility, but here I want to give you a sort of an analogy based on a random walk tourist, which I find might be intuitive. Although I guess in the current circumstance, it's a bit of feels like in our other era. But here it is. So here in this picture, each dot is a city, I, with a population of tourists, pi I, which is proportional to its size, okay? We're gonna say that these tourists are taking a random walk, and each person picks a destination at random based on their current location. So these transitions are pi to p from I to j. Now, one sort of scheme that we could make to allow these tourists to move is to say that that we're gonna move tourists by using full planes going back and forth between pairs of cities. Now let's think a little bit about what the number of people taking a plane between city I and j. Okay, so this will be let's see, I just want to make sure that I can see the chat window. I don't see it right now in case there are questions. So I guess, Torben, do you mind to just jump in if there's a question? I don't see the chat window right now. Just
stop you, yeah.
Perfect. So yes, the number of people taking a plane between I and j will be basically the number of people, tourists in this city times the fraction that go to city j. Okay, and basically reversibility says what I mentioned earlier, that the flow of tourists can be sustained by full planes going back and forth between pairs of cities. So this is this equation here. Okay, now one consequence of this reversibility is that the number of tourists in expectation in each city will stay constant over time. So going from reversibility to non-reversibility is essentially going to that more relaxed criterion for how to move tourists around, if that makes sense. Now we're just going to ask that basically we want the size, the number of tourists in a city to stay constant. So we want, if we think about it, it's just saying that the size pi j will be at the current step will be equal to the inflow of tourists coming. Now, if all the cities are the same size, same number of tourists, you can see an easy way to do this. So you just move people in a tour around the world like this, and this will keep if all the dots were the same size, that would work. Okay. Now what we want to do now is to move this to a more general setup where the size of the cities are different. The posterior distribution of each state that's in a discrete set, and we want a general scheme that works beyond the uniform distribution, obviously, if that makes sense. So basically, for a long time, so the first method that was discovered to build a reversible scheme with a prescribed stationary distribution was a reversible scheme. It was the Metropolis Hastings scheme, and it's basically been used for 60 plus years and is the basis of much of the general purpose MCMC. Now, if you think about it, this imposes basically, if there are n cities, it imposes order of n square constraints on these small p. The space of non-reversible walks is less constrained. It has order n constraints, so it opens up to more MCMC algorithms. Okay, and basically an important question in the last decade and more is basically, are there superior algorithms out there? And this has been known that this is the case for many cases. At the beginning, it was more toy examples with the so-called lifting construction by Diakonis et al. And later it was realized that this can be extended to, for example, many Riemann integrals. So, for example, the zigzag sampler or the bouncy particle samplers, they work for many Riemann integral with differentiability. But these are still sort of case-by-case things. There were few recipes before that that apply to any cases where Lebesgue integration is defined. So basically, so that brings us to this question, which is the center of this talk, which is, are there broadly applicable non-reversible algorithms that are provably and practically better than reversible ones? And again, sort of what I mean by broad applicability is that I'm interested in algorithms that apply whenever the Lebesgue integral is defined. And so this work is about this research with my student Saf Said and collaborator George Legianidis and Arnaud Doucet that shows that yes, this can be done, and we showed this. This is the case for a class of MCMC method called parallel tempering. And it turns out that the gap between reversible and unreversible is substantial in that setup. And so the talk is not about the bouncy, but you'll see that later that there's some PDMP construction that will make a surprise appearance later. But that's a new work on these non-reversible parallel tempering methods that we've been interested recently. So that's in the reviewing pipeline. So there's an archive that you can find from my webpage, a non-reversible parallel tempering, a scalable highly parallel MCMC scheme, if you're interested. So just a bit background on parallel tempering. So that's an old method from the 90s that was developed independently in the physics and the stats literature at the same time. And the input, in some sense, is a meta algorithm. So the input is an MCMC algorithm, and the output is another MCMC algorithm that's transformed into a sort of this new transform MCMC algorithm is often much more performant. So the first building block towards parallel tempering is this idea called annealing. So the idea is that instead of just looking at one problem, the posterior distribution, we're going to build a continuum of distributions or of problems indexed by an annealing parameter, let's call it beta, from 0 to 1. So one common construction in the Bayesian setup is to say, I'm not going to anneal the prior to make sure that it's always a probability distribution. And I'm going to take the likelihood and exponentiate it. And then you get essentially a series of, if it's in Rn densities, but in general, any measure that are often going from beta equals 0, which is easy. So beta equals 0 with this construction is just the prior. So in the Bayesian setup, the really interesting thing here is that we can actually sample for IID from the prior often. So we have this easy end, and the other end of that spectrum is the posterior, which is hard, and the quantity of interest. So what is interesting with this construction is that basically there's no assumption made on X. So basically I just assume that I factorize these, but each of these factors, I don't care about what is this input X, and I can always do that annealing construction whenever the Lebesgue integral is defined. And how do we take now the sequence of, or this continuum of distribution and make it into a parallel tempering algorithm? It's done with augmentation of the space. So instead of having one copy of the state space, so one tree that we maintain in memory, we have maybe three copies. Okay, so where each of those are using one of these annealed distribution. Okay, so big N here will be the number of copies of the state space that I keep in memory. Just start with something simple where it's just the real line. Let's say we're just doing a univariate sampling where, of course, we wouldn't use MCMC, but just to illustrate, let's imagine this is the case. Then our sampler keeps three real numbers in memory. So the X are the current states. Okay, so we have these three states in memory. Now, basically, linking it with this, this idea of annealing. So now I have 3 copies of the 3 distributions that are, I build an augmented space where the 3 distributions are independent. The one on top is the posterior distribution, the one in the middle is an anneal version, and the one at the bottom is the prior. Okay, so this is just this. So for simplicity, I'm just taking these 3 points in the continuum of distributions that interpolate between prior to posterior. And let's start with assuming they're equally spaced. But as we'll see, it will actually become a key issue is equally spaced is not a good idea in practice. So often, so we'll talk about a methodology to pick the sequence of betas that interpolate well between prior to posterior. So with parallel tempering, still doing background on classical stuff, I'm just going to walk you over a few steps of the parallel tempering algorithm. At the first iteration, we do what we call local exploration. So we basically, for each of these chains, we apply an MCMC algorithm. So that's why I said it's a meta algorithm. So we assume there's an algorithm to explore each of those targets. And we do them independently. So basically, here's an example. We successfully jumped. Here, we didn't manage to jump. That was rejected. And here at the bottom, we sample a new IID sample from the prior. Okay, so this is the local exploration. Now, the communication is where we actually make use of having several copies of these states. We propose a swap. Okay, so a swap is just basically saying this state, I'm going to propose to move it to a different annealing parameter, and vice versa for this one. Okay, so it's a deterministic proposal, and then to maintain this exact approximation of property, so a law of large number, we accept or reject this swap using the Metropolis-Hastings ratio. Okay, so that's it. Just basically involves these 2 anneal distributions before and after the swap. So I'm going to use that visualization for this, where basically what I did here is I proposed between these 2 chains, and I succeeded to do a swap. So I have these green arrow, and then I rejected the swap, or I did not actually propose a swap here. So I stay at the same state on this one. Okay, so that's the communication stage. And then I would do another local explorations iteration, and then another communication, this time between these 2. And then another local exploration. And then here I try to communicate between these 2 and I reject it. So here my communication didn't move anything at all. Okay, so in order for this to work, you need more chains. So here's another example for 8 chain, the same visualization. And basically, if we fix the number of chains and increase the dimensions, the swap acceptance probability drops to 0. So basically, the solution is to use more and more chains. So in real problem, you might need quite a lot of these chains. And the good news is that if I make these chain close in the space of annealing parameter, I can actually make the acceptance probability to be made, I can make it arbitrarily close to 1. Okay. The bad news is this phenomenon called Goldilocks curse, which has been documented for a while, which is that if you have a reversible parallel tempering, and I'll describe what I mean by this soon. It's essentially the algorithm I described so far. Adding a few parallel chain is beneficial, but then after a point, adding more chain becomes actually harmful, which is a lost opportunity because we do need massively parallel MCMC, and parallel tempering would otherwise be a very suitable algorithm for parallelization and distribution. So in terms of distribution, there's this nice idea that even if these chains are in different machines, they can communicate very efficiently because instead of exchanging states, X, which are quite large, they can just exchange annealing parameters. So you can actually do distributed parallel tempering over a constant network cost, constant in terms of the dimensionality of the problem. So it's really a lost opportunity that this phenomenon that adding more chain is eventually harmful. And the reason for it is a diffusive behavior. Essentially, if you have n chains, they require essentially n square step to carry from prior to posterior. And formally, that's not enough to offset the parallelization gain, which are order n. So eventually, you get that very frustrating situation that maybe you have more core available. You would like to throw more compute at it, but adding more core will actually decrease the performance, will actually make things slower. So that's very frustrating. So the state of the art is basically say, we're gonna adapt the number of chain n and also the spacings, betas. So there's a long line of work, both in the physics and the stats literature, Kohn and Kopf and Ashade et al., for example, which target an acceptance probability based on high-dimensional asymptotics of the state space. And basically, you add chains which increase the acceptance rate until you get to that 0.23, and don't go further, because at this point it will make the algorithm slower. Basically, our theoretical result is that Goldilocks curves disappear essentially, or when you have a non-reversible parallel tempering scheme. What I mean by this is that with non-reversible parallel tempering, increasing the number of cores and the number of chains never hurts, essentially. There will be a diminishing return at some point, but it will not make the simulation slower. But moreover, non-reversible parallel tempering provably dominate reversible parallel tempering for any number of chains. Okay, so this is nice that we have both asymptotic and non-asymptotic results. So in order to describe the result, let me go over the difference between reversible and non-reversible parallel tempering. So basically, in a given communication round, where we do these swaps, we attempt to swap as many consecutive but disjoint pairs of chains as possible in parallel. Okay, so the way to do this is to use alternating pair like this. So let's denote the swap indices by I and I plus 1. Okay, so these are the pairs that I propose a swap, which may or may not be accepted. Now, the key is how I'm going to alternate between different kinds of swaps. So let's introduce the even swap, where we pick swap pairs such that I is even. Okay, so we always go for like swapping as many things as possible, but we do it with pair I and I plus 1 such that I is even. Whereas the odd swap we pick swap pairs such that I is odd. Okay, so in this visualization here, E here is an even swap, and O here is an odd swap. So you see, it's another set of pairs that I propose swap. I want them to be disjoint so that I can do all of them in parallel. Does that make sense? So one way to differentiate then between reversible and non-reversible scheme is a very simple distinction that looks trivial a priori, but turns out is very important. Basically, in reversible parallel tempering, we stochastically pick E or O, even or odd, using a coin flip. So you get something like that. So E, O, so you have repeats. Whereas for non-reversible PT, we deterministically alternate between E and O. Okay, so E, O. So these two algorithms, though, it's been known for a long time that there's these two flavors, and physicists in particular have documented preferring the non-reversible scheme, but mostly on sort of algorithmic grounds. What was a big surprise with this project is that this seemingly minor detail actually has a profound impact on the behavior of the parallel tempering algorithm. So just to recapitulate, what basically we're saying is that we compare these two schemes. So SEO, stochastic stochastically picking E and O, which is reversible, and non-reversible parallel tempering, where deterministically alternate between E and O.
Alex, there's a question.
Great, yeah.
Unmute the. There we go. Shaheen, you should be able to speak now.
Yeah. There's just something I find weird. When you deterministically alter between even and odd, this is non-reversible.
Exactly. So it's a non-reversible scheme, and that will be the key of the analysis. That it still has a lot of large numbers, so it still satisfies our requirement that we can approximate expectation with respect to it. A lot of the theoretical ground used to analyze MCMC goes out of the window because often the reversibility is assumed, but there's more and more tools to analyze non-reversible schemes. So that's what we're leveraging here. But yeah, thanks for the question. Did I get the question right?
Yeah, I was puzzled because in my intuition, if you just alternate, you make it more reversible. So I just have a bad intuition.
Yeah, no, it's surprising. But yes, whenever you have a situation where you have an inventory of kernels and you pick one at random, ID, that will preserve reversibility. But whenever you have a deterministic alternation, that you're not guaranteed to get reversibility. And in fact, what's interesting is that a lot of the current work in non-reversible samplers, often you can boil it down to just this, that an alternation between, a deterministic alternation between two reversible kernels. So that's something that people have noticed in the literature. If you look at non-reversible flavors of HMC or lifting, these are a skew balance in general. This is always can be viewed as deterministic alternation of reversible kernels. So that's the same idea here.
Okay, thanks.
Yeah, thank you. Other questions? Great. So then let's continue. So what we're saying here is that we compare these two schemes. So SEO, which is reversible, and DEO, which is non-reversible. And we, under certain assumption, of course, we can prove a domination result. Okay. So in order to talk about domination, I need to tell you more about what I mean for, in our setup, for one MCMC algorithm to be better than another one. Okay. And since we have a meta algorithm where we assume nothing on X, a lot of the classical tools for looking at performance of MCMC is a bit harder to apply. So what we go for is a notion of performance, which was developed by the physics literature for parallel tempering, which an interesting way to think about it, I find, is thinking about it as a random restart. Okay, so basically, I remind you, so the setup we're interested in, so we're in a distributed computing setup, so we can summon, let's say, as many machines as we want. Okay, so basically, it's a parallelized computation model where basically one step in this picture is always the same cost, no matter how many rows there are. Okay, and let's assume also that the prior is special and that we get IID samples. Okay, so now imagine a prior that at each time you sample from the prior, you get a new unique color. Okay, that sort of marks the states. Now, a random restart, basically, you can think about it as when the posterior sees a new color. Okay, so at the prior here, there's always a new unique color that's being created, and after a while, it may either sort of go back to the prior, and this color never gets seen by the posterior chain, or in some cases, it will percolate all the way back to the posterior. So each time we see a new color, this is sort of an opportunity to move far in the state space. If the prior took us to a different mode, that new color is something that maybe we would have never been able to do with just local exploration. Okay, so this is a random restart, and the restart rate tau is the fraction of MCMC iteration that are random restarts. Fraction of time you see a new color. So our non-asymptotic result shows that if we define this tau for a certain number of chain, and for the non-reversible version, it will be greater than the reversible version for all number of chain greater than 1. Okay, so that's basically saying never use reversible. It's a simple algorithmic change, and this will make performance better. Moreover, what we have is that for a number of chain n, if it's large enough, then this function tau, now seen as a function of n, will be increasing. Okay, so it will be increasing. It will not go to 1. So there will be a diminishing return at some point, but it will not go down. Whereas for reversible scheme, it will go to 0. So that's the Goldilocks curve, that at some point there will be a sweet spot where you want to stop adding more machines. Here, what I want you to open your mind for now is using models for algorithms. Okay, so we are all very comfortable for using models for data, but somehow when people are less comfortable when introducing model for algorithms. So what are our assumptions? So there's stationarity, which is kind of a standard one, but not great. But there's another one which is stronger, and really what I think about it is a model for algorithms. So it's called efficient local exploration, and it tells us that if I sampled a configuration according to the state space, the distribution at temperature or annealing parameter beta, then and I do an exploration kernel, so I apply my MCMC scheme, then the likelihood the log likelihoods are evaluated at the point before and after are independent. Okay, so this seems a very strong assumption, and it is. What I want to bring your attention to is, first, it is not as crazy as assuming that X beta and Y beta are independent. Assuming that X beta and Y independent would make basically parallel tampering not interesting at all in that setup, because it would say you can have ID sample from the posterior. Here we're just saying that basically if you're able to explore well one of these mode and explore well this other mode, and their energy profile or their log likelihood profile looks the same for each of those, then you approximately satisfy that condition. Okay, so I can talk more about this maybe in the question at the end, but I will say right away that we don't think this assumption holds exactly for real models, but we think it holds approximately for many interesting models. And we really view it as basically the same idea as building models for data. Even if they're wrong, they can be useful because they can be checked empirically. And that's what we did. And I'll show you some results later that these assumptions are checkable and that they actually are well approximated in real problems. We also have a new direction that relaxed this quite a bit. So I'll just give you a hint on this at the end. But basically, if you indulge me on these ELE assumption, effective local exploration, then basically our non-asymptotic result unlocks with these assumptions a new type of asymptotic analysis for parallel tampering. What do I mean by this? Well, if we look at typical asymptotic regimes, there are things like letting the number of data points go to infinity, or letting the number of parameters go infinity, or letting the running time of the algorithm, e.g. the number of Monte Carlo iteration, go to infinity. Here we're taking a road less traveled, where we let the number of cores available go to infinity. And arguably that's more relevant now than letting the time go to infinity. Basically, to understand a bit our result, let's talk about a switch in perspective. So I mentioned this practical consideration before, that when a swap is accepted, what we actually do, so each machine always keep the same sort of copy of the state, and the machines, they do not swap, they do not transmit the state over the network, which would be quite expensive. They just tell to each other, now you're responsible for my annealing parameter, and you're responsible for mine. Okay, and what this allows us to do in analysis, in an analytic point of view, is that basically let's instead focus on the marginal behavior of the sequence of annealing parameters that are assigned to one machine. Okay, and basically in that picture that corresponds to a bold trajectory here. So a machine here will basically be assigned these states in that subset of state in that graph. And what I want to do now is to just think about that path for now. Think about just that path, where on the x-axis now we're going to move to a continuum. So the full continuum of distribution interpolating from prior to posterior, and here n is the MCMC iteration. Okay, so basically what we found is that for reversible parallel tempering, the limit, weak limit, as the number of chains, intermediate chain goes to infinity, is a diffusion for the reversible parallel tempering algorithm, and is qualitatively different in a non-reversible scheme. It's a piecewise deterministic Markov process, which look like this. You basically have persistent behavior in the space of annealing parameter, and then either you bounce at the endpoint, or you might bounce in intermediate points when a swap is rejected. Okay, so let's look at that a little bit more details. So I'll just, Samuel already did an introduction on PDMP, so I'll go over that quickly. So here I emphasize that we don't use PDMP for the implementation, but rather for the analysis of the algorithm. But basically the ingredient for a PDMP is a deterministic flow, let's call it phi, and at random time, determined by an inhomogeneous Poisson process with rate lambda, you have a jump. Okay, so the jump is given by a transition Q here. Okay, so basically I mentioned that earlier, that this I just want to reemphasize it, that this deterministic even odd swap is not a new algorithm. It's an algorithm that exists in the physics literature. But basically the surprise here is that it was incorrectly assumed to have also diffuse behavior. So it was sort of incorrectly assumed to suffer from Goldilocks curves. So what we showed is that it's not the case, essentially. Now, what is the intuition for this? The intuition is there's a persistence of motion that's induced just by the combinatorics of deterministically alternating between even and odd swap. Okay, so I guess I found no better way for this than to just stare at the picture a little bit. If you look at the picture a little bit, and you have this deterministic alteration of odd and even swap, you see that if things are always accepted, this creates a straight line where the directionality is basically either going up in the space of annealing parameter or going down. Okay, and basically we also made that observation that rejection probability for one swap goes to 1 as the number of chain goes to infinity. But you have more and more of these chains, so this has basically a Poisson behavior. Okay, so that's the intuition. And basically, as soon as though you hit one of these rejection of a proposed swap, you get basically a one-dimensional bounce in the space of parameters. Okay, so it turns out though that basically to formalize this, we need a PDMP on a slightly augmented space that looks not only at the space of annealing parameters, but also at that direction sort of notion, epsilon, which is either going up or down in the space of annealing parameters. And that basically describes the limiting PDMP up to this function lambda. And that's where it gets interesting in my opinion. Okay, so this function lambda, in some sense, it encodes in a certain part of the annealing parameter space how hard it is to do bounds there. Okay, and it's a function that it turns out we can estimate it quite well. And if let's visualize it at this fashion. So let's say that, so this axis here is the space of annealing parameters. I have a discrete set of chains here. And this function lambda basically tells me how hard is it to do swap in that local neighborhood of the space of annealing parameter. Okay, so if we take that function and normalize it by this area, it basically we get a distribution over the parameters where swaps are rejected, if you want an interpretation. So for example, for an Ising model, this function lambda has a peak at the critical temperature. So that makes sense. Now, linking this to the theory that we had, the nice thing is that this limit, I said already that this function, this restart rate as n goes to infinity is increasing and converges to a value less than 1. Well, this value can actually be written as 1 over 2 plus 2 times the area of the curve of this function lambda, the parameter of the PDMP, the limiting PDMP. So basically, so in some sense, this is both a positive result because this gives us a form for this, but also a negative result in that it gives us sort of a barrier, that a fundamental barrier that even non-reversible parallel tempering will not break. But so we have some current work where we basically we have some ideas that to design new algorithm inspired based on this that could go beyond this, that could I think about it more as a sound barrier than the speed of light. That's something that we can do better than this. Something that I want to talk briefly, so I'm almost done here, is that what I really like about this theory is that it has practical application. So I think maybe the most important problem, if you go at home and you have to implement parallel tempering, you'll find that for a finite number of chains, this annealing schedule actually matters. And setting it up in the reversible setup is hard because you have to increase the number n and use the stochastic update scheme, which sometimes have stability issues. And you cannot go beyond this critical n because performance will be really bad. So in practice, setting these annealing parameters is awkward right now. And what the non-reversible theory gives us is a very practical scheme for adapting these annealing, this so-called annealing schedule, sequence of beta. And basically, there's a sort of a part of this result which is not surprising, which is basically that you should pick a schedule which you can show is equivalently doing having the same acceptance rate between consecutive chains. The interesting bit is a new way for doing this. So what we do is we estimate this lambda while we sample, and I'll tell you how to do this in a second. And then we pick a schedule such that the area under the curve lambda between chain is constant. So that's very easy to do. We just use a univariate numerical algorithm and find these sequence of annealing parameters. But of course, it all depends on being able to approximate lambda. So how do we do this? So here the blue dots were the optimal schedule, and the green, I remind you, is the area under the curve of lambda, which is the parameter, the rate parameter of the limiting PDMP. So how do we estimate a lambda? And that's interesting, I think, because often when we study MCMC, the quantities that come out of it are hard to estimate. Things like effective sample size or spectral gap or mixing time, they are hard to get a handle on in practice. In contrast, lambda is easy. So basically, lambda, you can estimate it by basically taking the expectation over the absolute value of a difference of log likelihood. So here, imagine x beta and y beta are distributed according to the distribution at parameter beta. And imagine I had 2 copies of this, and I average over the absolute value difference in log likelihood. Okay, so this is something from the MCMC trace you can do, and that's basically the idea of the adaptation schedule. Okay, so we go over rounds. So the rounds use an exponential number of MCMC iterations. So first, 1 MCMC iteration, we estimate lambda, we estimate what is the spacing, and then we do 2 iterations, we do the same thing, 4 iterations. So as the round goes increases, we see that each of these curves, which is the annealing parameter, is set to a certain schedule. And in practice, so we can compare this to existing schemes for adapting parallel tempering based on reversible dynamics. And we get huge gains from two sources. One of them is adaptation is much faster, and also the sampling is, it agrees with theory that it's much more efficient. Then it dominates the non-reversible scheme, the reversible scheme. So I promise I would say just a few words on the ELE assumption. So here it is. So basically, as I mentioned, it's a useful model, ELE, because what we did, for example, is we looked at the Ising model and we estimated that lambda. But each curve here, we use exploration schemes that are violating more and more the ELE assumption. So here we do, the one here approximates well the ELE assumption because it samples 32 times each node in the Ising graph, whereas this one here only samples them half the graph. Okay, and here's the estimated lambda. And as you can see, except in the degenerate case where you don't sample at all the configuration, we get basically the same function lambda. So this means it's, at least in this case, very robust to ELE. We have also a conjecture that the analysis for the reversible case is, I don't see a way to relax the ELE assumption, but for the non-reversible scheme, we think there's a way to relax the ELE assumption. So just in the interest of time, I'll skip this for now. I'll just say briefly also, if you're more working on the applied side of things, we're also working on ways to make this theory widely applicable. So parallel tempering, if you're looking at hard sampling problem like multimodal and discrete space, they're extremely powerful. So for example, there was this review paper recently and that looked at a huge range of different MCMC methods. It was not like trying to sort of get a specific horse to win. It was really trying many things and seeing what works and mostly for dynamical system problems. And then it found that only parallel tempering basically was able to work on challenging problems. Even HMC by itself is not enough for these hard problems. But there are practical challenges to get parallel tempering to work in practice. So coding MCMC is error prone, and it's even trickier with parallel and distributed parallel tempering because you have to set up that distribution continuum, you have to set up these exploration kernel for each annealing parameter, you have to do adaptation. There's a lot of moving parts, so often in practice, people don't get around to try it, even though it's quite a powerful trick. So we built a new ProStick programming language that's really centered around being able to set up automatically parallel tempering, and more generally, Prome's inference method that rely on a continuum of distribution instead of just one distribution. But where this continuum is created automatically, you don't have to do it yourself. So the notation looks a lot like bugs or math notation, but it also has an open type system where basically the random variable can be not only in RD, but they can be things like trees and matchings and different structures. And if you're interested, you can look on my webpage to download the copy. It's open source, and there's some documentation, and we're happy to help people that are interested to use it. Just drop me an email. Just like a very quick demonstration of where this is used right now. So this is a project with BC Cancer where we infer trees over a large collection of single cells. So we're talking about thousands of individual cells. The data is the full genome, and the combinatorial space is a novel thing. So it turns out that classical phylogenetic model need to be adapted to the cancer setups. So we implemented some novel tree distributions and MCMC algorithms and so on. And then we use this ProStick programming language and non-reversible parallel tempering to do inference. And what we found, for example, so and just like using off-the-shelf EC2 nodes with 72 cores, 500 parallel chain, just in the trace plot, you can already see that there's the parallel tempering will find trees that are 100 times more likely compared to reversible NCMC. So just a quick vignette to try to convince you that this is a practical thing that can be used. So basically, some pointers here, and I'm happy to take some questions.
Thanks a lot, Alex. That was really nice, really interesting talk, both kind of from a theoretical point of view and also from the application side. Before we move to questions, I think it would be nice if people maybe turn their cameras on for the last question.
Oh, yes, yes.
Session.
Oh, let's see.
And then I'm going to start with my first question. So how much do these parallel tempering ideas depend on the Markov kernel that you actually choose to run the individual change on each temperature level? Is it enough to just do kind of simple, random walk metropolis, or what do you normally use and why?
Yeah. So can you see me now?
Yeah, perfect.
Perfect. Can you also see the screen?
Yeah.
I didn't realize that, so I was cut the whole time. Sorry, I'm a bit of a Luddite. But okay, so the question is, yeah, how much the theory relies on what we call, I guess, the exploration kernel. And so the answer is, for this current incarnation of the paper, is how well you can approximate this result. So what this result tells you, again, is basically, so imagine that the problem of interest is something that looks like this. So this seems like a sketch, but it's actually relevant in some cases where we have, let's say, one mode here and one mode here. And kind of a case where this occurs, for example, if you're doing Bayesian inference over a mixture mole and you have a mole that is not sort of resistant to label switching, you have sort of, by permuting the labels, you have like these modes that are each at a permutation of the parameters. And basically, to get a full picture of, for example, the evidence, you want to be able to explore these different modes, okay? So what this assumption tells us is that you don't need your exploration kernel to be able to switch mode, but you need to be able to get a good estimate of one statistic. Okay, so in general, when you have NCMC scheme, you need to worry about any test function, right? You need to be able to say, okay, I have a good ESS for the mean of this marginal, this marginal, this marginal, this marginal. Okay, what this tells us here is that you only need to care about one statistics, which is basically composing the state with the log likelihood. Okay, if your scheme allows you to do this, then you're in a situation where you're approximating well this efficient local exploration. So, for example, HNC will be quite good at exploring one mode of, and it might not be good at jumping from one mode to the other one, but it will give you a good, under certain assumption, it's not always true, but under certain cases, a good idea of what the posterior distribution for that one statistic. And that's something you can monitor, right? You can look at the SS of this just one statistic, make sure that you do enough exploration around that you approximate that well, and then combine it with non-reversible parallel tempering. Does that answer the question?
I'd like to ask, I see it's mentioned in the paper a little bit. Did you guys look at the infinite swapping parallel tempering stuff at all? Because I think that's sort of also very interesting.
Yeah. So we looked at it and we didn't. So just to briefly mention, so this is a bit maybe connected to this slide here that I was talking about different asymptotic regime. So basically, that's actually another asymptotic regime where instead of it's related to the running time, where we say a certain time goes to infinity, and well, this other group look at this, so they look at basically instead of letting the compute time go to infinity, if our process is embedded in a process time, what if we make this go to infinity. So what if we propose swap more and more often relative to, let's say, a Langevin dynamics that is the exploration kernel? And that's also a very interesting direction in parallel tempering literature right now. I don't have a great answer on like how it can interact with this stuff we've developed, but it seems like a natural thing to explore, I think, these two directions, yeah, simultaneously.
Thanks.
So if I may just ask a follow-up question on that. So how many MCMC steps do you do per kind of between swaps?
Yes. So this is, I went a bit fast on this picture here. Okay. So this picture here is essentially.
I
don't think we can see your slides right now. Sorry.
Oh, sorry. Okay. Let me do this. Is that better?
If you're on the references, then yes, but otherwise.
Oh, okay. Resume share.
Oh, there we go.
Okay, okay.
Yeah, something's happening now.
Okay, thank you. So basically, this is essentially the number of local exploration that we do between two swaps. Okay.
Okay. Yeah.
And so this picture actually tells something more, which is that, okay, so with this version of the theory, what it tells you, naively, what it would tell you is that you should only do exploration, you should only propose a swap once you've explored enough that you have an approximately independent sample from the energy, okay? So that's sort of what comes out of the theory. This picture here tells you that somehow things are nicer than that. That here what we're doing, we're being more and more aggressive in doing swaps. And here at 0.5, we're doing swaps even before we've actually touched once every Ising node in the grid. And somehow we found that it was a surprise that the lambda function is still well approximated, the adaptation schedule goes as it did, and things like, and the actual number of restart rate is similar. And so that was really intriguing. So this is where maybe I can tell you a bit more about that conjecture, which is that basically, so this I don't have a great way to explain it yet, but basically, my conjecture is that in the non-reversible parallel tempering, we will be able to relax quite a bit that effective local exploration hypothesis. And this is because if we look at the limit where there's many chains, and we look at a typical picture of what these visualization look like, it will look like a Poisson process in 2 dimensions. There will be either no swap rejected at all, or 1 swap rejected at all, okay? So here we see a picture where there was 1 swap rejected. So basically, in that picture, you can see that even though a swap was rejected, in that neighborhood, no 2 pairs of chain interact more than once. So even those 2 that was rejected, since they go in parting direction, they will not interact again. So what this means is that instead of asking for all the energies to be independent, we can only ask them to be independent from a point where they meet to the point where they meet again later on. But the point where they meet later on will not go to 0, in contrast to reversible parallel tempering. So this means that my conjecture is that as long as you have geometric ergodicity of your exploration kernel, you will be able to recover that PDMP behavior. It's just a conjecture at this point, but that's why we think the conditions are not as I hope that they can be relaxed in the non-reversible case.
Yeah, thanks a lot. That's quite interesting, actually. I think about that as well. Are there any further questions? That seems to not be the case. Then let me thank Alex once more and all the other speakers of the entire conference.